Hello everyone and welcome back to another episode on complete reference to CUDA programming. In previous episode, we have seen how 4 number of threads can be used to work on 8 number of elements of the array. So if you recall, I said there are 4 threads in a thread block and corresponding IDs are 0, 1, 2, 3, right? And in first iteration, they are going to work on corresponding array elements. So thread 0 to 3 will work on the array elements 0 to 3. After they finish that operation, now they'll move towards the next 4 elements by adding the jump size or the stride equal to 4, and they'll perform addition on next 4 elements. Now, if I'm having another elements in the array, then again the logic is going to be the same. So these first 4 threads are going to work on these next 4 elements from 4 to 7, and later on again they will be added with the stride equal to 4, and again it will perform the same operation. So now we can use 4 number of threads to any number of array elements. Now let's try to understand in the code how we can implement this. So again, I'm using a simple vector addition code here. So I'm considering n equal to 1024 here. Then I'm creating 3 arrays, array pointers here, HA, HB and HC, and I'm allocating memory on the CPU side. So A and B will be our input and C array is going to hold our output from the CPU. So there are going to be 2 functions. One is going to perform vector addition on CPU side and other is a kernel that is going to perform vector addition on GPU side. So here this array is going to hold output from the GPU. So whenever I'm going to perform the vector addition on GPU side, the output I'm taking back on the CPU side and I'm using this pointer to hold that array. And once we finish all these CPU function and GPU function, then I'm going to compare whether the results are correct or not. So if results are correct, then only we can go on check with the performance. So this is about the CPU side memory allocation. Now GPU side, I'm going to declare 3 variables again for holding input, that is array A, B, and to hold output, that is array C. Here I'm simply initializing those arrays. So A and B are initialized with 2, C and HRC will be initialized to 0. Here I'm calling vector addition on CPU side. So you can observe here, I'm just passing here CPU arrays and the size of the array, that function. And if you see the simple function, it looks like this. So I equal to 0 to n, C of I equal to A of I plus B of I. Now this addition is already performed on CPU side and we already recorded how much time it required to perform that computation. Now let's try to first allocate memory on the GPU side. So to do that, I'm using CUDA malloc function, and for 3 arrays I'm allocating memory of size n into size of int, that is integer arrays are allocated. Then I have to transfer the data. So HA is the source and DA is the destination. So I'm transferring the data from host to device using CUDA memcopy. So I'll transfer HA into DA, HB into DB, and HRC into PC. Again, this third function is redundant. It is not required in this context, but there are many cases where we have to copy the output array initialization also, and that's why I just copied here. So if you want, you can comment this out also. Next, I'm calling this vector addition kernel using single block. So this is our original kernel, and you can observe here, I'm passing first parameter as 1. That means I want only one block and there are going to be 1024 threads. And the parameters I'm passing here are the GPU pointers, DA, DB and DC, and the size of the array. So this is the vector addition kernel using single block I'm calling. Now let's explore what is this kernel is performing. So this is the kernel vec addition using single block, and you can see here I am creating a TID variable that is going to be private for every thread and which is going to hold thread idx.x. Note that this thread id x dot is going to return a local thread id. So it won't matter here because we are launching only one block of threads, so of 1024 in size. So this tid variable is going to hold corresponding threads id. Now here it is going to be little bit different. Earlier in previous one of the episode, I mentioned that we try to execute the same vector addition program, but where number of threads equal to n, right? So number of threads equal to the size of array. But now in this case, we have 1024 number of threads and we have n equal to 2048. So in this case, what I'll do, I'll introduce a for loop to ensure that striding concept. So in this for loop, if you observe, I is initialized with tid. So for 1024 threads, I value in the first iteration is going to be the corresponding thread id. Then we are checking I must be less than n. So I should not pass beyond that n value to avoid the out of memory access by the thread, right? So it is just we are restricting number of threads to limit themselves less than n number of n size of the array. And once it performs the addition on tid, then we are going to increase I plus equal to blockdim.x, that is nothing but total number of threads. So let's take one example. When I equal to 0, what happens? C of 0 equal to A of 0 plus B of 0. So first addition is performed by thread 0 with the 0 index. Now once it is done, so it will check whether I is less than n or not now. So 0 is less than n, so it will go on perform I plus equal to blockdim.x. And in our case, blockdim.x is nothing but 1024. So now I becomes 1024. Now same thread is going to perform addition on C of 1024 equal to A of 1024 plus B of 1024, right? And same way, if I take another thread, thread 1, so it will perform initially addition on C of 1 equal to A of 1 plus B of 1. In next iteration, it is going to perform addition of C of 1025 equal to A of 1025 plus B of 1025. And that will happen for all the threads. Note that here, if I increase the number of elements in array equal to 4096, in that case also this program will work fine without any error, because now what will happen, I equal to 0 for thread id equal to 0 and I less than 4096, right? So every time it is going to increment to that number of threads and it will check whether it is less than n or not, right? So when I n equal to 4096, so thread 0 will perform 4 additions on 0th element, then 1024th element, and then 2046th elements, and finally 3070 elements, right? So this is how thread 0 will perform, and accordingly you can consider thread 1 will perform the addition on first element, then 1025th element, then it will perform addition on 2047th element, and finally it will perform addition on 3071th element. So this is how it is going to perform addition, and we can generalize it for the remaining threads. So as size of n goes increasing, the work per thread is going to increase here. So this is how we have to implement this kernel where number of threads are less than number of elements. Now once I complete that kernel execution part, then I am copying back results from GPU memory to CPU memory. Note that while copying, now I am storing results in this HR underscore C, right? And finally, here I am just simply writing a loop to check variable, check whether the results are correct or not. So I am comparing HR underscore C and H underscore C. These are the arrays. So here I am having CPU's output and here I am having GPU's output. So if both results are matching, then only we are going to look into the performance improvements. Finally, the memory gets deallocated here for the CPU side using free function and for the GPU side using CUDA free function. So now let's try to execute and see the performance difference. So here I have already copied the code on this cloud instance and let's execute and see the performance. So you can see here I'm getting performance of 4.4 times, right? That is my speed up. So here I consider number of elements equal to 2 to the power 24 and the same kernel is there. I have not modified it, and number of threads per block equal to I'm having 1024. If I reduce that size to let's say only 2048 or 4096, you won't be able to see much improvement in the performance because we are launching very few threads and task is also very less, and that's the reason you won't be able to see the performance improvement. And now if I increasing the size of arrays to 2 to the power 24, here I'll be able to see the performance improvement, and that is almost 4.45 times better. But even note that this performance is again very less because I'm having many cores available in my GPU, but out of which I'm launching only one thread block of size 1024, and this is going to exploit only the one streaming multiprocessor of the GPU, and rest of the streaming multiprocessors on the GPU are unutilized, right? So though we are observing here some about performance improvement, but still we are not fully utilizing the GPU's capacity. So we'll see all those things, how to further improve this vector addition code by launching multiple thread blocks in the next episode. Thank you.